In today's lesson, we are going to be looking at the rule of sum. So we've already kind of looked at something like this in the past when we've looked at simple probabilities, and what we're going to do is we're going to tie it into our counting principle, the fundamental counting principle that we've looked at in factorials and permutations. So we're just kind of extending again and adding on to the concepts that we already know. So the rule of sum, or you could also call it OR, because again, this is where we will see this come up when we see kind of OR in our questions. Again, remember when we see OR, and we've talked about this in certain probabilities or simple probabilities, that OR just means plus or addition. So we want to recall that when a first action can be performed in m ways, so first action in m ways, and a second action can be performed in n ways, but the two actions cannot be performed together. So this is a key thing. The two actions cannot be performed together. Then there are m plus n ways to perform the action. So we've seen stuff like this in the past, in particular when we're talking about two actions that cannot be performed together. This we've seen done as mutually exclusive, where two actions cannot be performed together, there's no overlap, they're two separate events, we add them together. That's the same thing when we look at the rule of sum. So let's look at a couple of examples. So in a deck of cards, how many ways are there to select a red card or a black ace? So again, we're not dealing with probability in this case, we're just looking at how many ways, or in terms of counting. We're basically counting. So a red face card, there are 3 face cards per suit, and there are 2 red suits, so there are 6 cards. For a black ace, again, there's 1 ace per suit, there's 2 black suits, so there's 2 black aces, or 2 cards. So in total, how many red face cards or black aces? How many ways to select it? Well, there are 8 total ways. Or there are 8 total cards that I could pick that would suit this scenario. If we kind of extend this, so let's say that Jordan has 12 DVDs, 5 horror, 3 action, and 4 comedies. How many ways can he choose one movie from each category? So reading this question, because it's saying from each category, this could be the same thing, or it could be read the same way as saying and, right? 1 movie from horror, and 1 movie from action, and 1 comedy, right? So 1 from each category, in this case, means and. And we've talked about this in the previous lessons. If I'm going to figure this out, I can use my slot method. So we have 1 spot for horror, 1 spot for action, and 1 spot for comedy. Because it's and, we're going to be multiplying these together. So we have 5 options for horror, 3 options for action, 4 options for comedy. Add these, or multiply these all together, and I get 60 ways. So there's 60 ways I can choose 1 movie from each category. B, if he can only choose 2 movies from different categories, how many choices does he have? So this is where it's going to kind of mix it up a bit. So the key thing is I'm choosing 2 movies, and they have to be from different categories. So that means 1 movie's from one category, 1's from another. So in this case, my options are or I have a couple different scenarios. So case 1, I'm choosing a horror movie and I'm choosing an action movie. I have 5 horror times 3 action. So there are 15 ways in this scenario. In the second scenario, I'm picking horror again, and I'm picking a comedy in this case. So still the 2 different scenarios. 5 horror, 4 comedy. So in this case, there are 20 ways. 20 ways I can select a horror and a comedy. And in the third and final case, I'm looking at action movies and comedy movies. There's 3 action, 4 comedy. This works out to 12 ways. Because all 3 scenarios or all 3 cases belong to this overall question, right? Because choosing 2 movies from different categories, these are the 3 cases I could have. So I could have case 1, or case 2, or case 3. What I then have to do is add up all of these ways. So 15 ways plus 20 ways plus 12 ways. I get 47 ways that I can choose 2 movies from different categories. So therefore, there are 47 ways to choose 2 movies from different categories. Example 3, at an international conference, in how many arrangements could the country's flags be flown if A, 7, 8, or 9 countries attend? So the key thing is I'm looking at 3 different scenarios, and they all can't happen at the same time because we talk about this or. And this or means plus. So that means I have 3 different cases that I have to look at. Case 1, I'm going to look at 7 countries. And if I have 7 countries laid out, or 7 flags in a row, the number of ways that I can arrange it, if we remember back to a previous lesson, is 7 factorial. Because if I have 7 countries, that means I have in 7 spots. So 1, 2, 3, 4, 5, 6, 7. There's 7 options for the first one, 6 for the second, 5, 4, 3, 2, and 1. So 7 factorial, which works out to 5,040 ways that I can arrange 7 countries or 7 flags. In case 2, 8 countries, it's going to be the same idea, but 8 factorial instead, because now I have 8 objects that I need to arrange in 8 ways. Or if I wanted to, I could say 8 pick 8, right? Or 8p8, because again, order matters in this case. But again, we know, or we should know from our previous lesson, that 8p8 is just the same thing as saying 8 factorial. So on our calculator, we should get 40,320. Our third case is going to be 9 countries. And again, same idea. 9 factorial, 9p9, 362,880. So these are the 3 cases that I'm looking at. They all can't happen at the same time, so I have to add up all of my cases together to get the total number of ways that these countries' flags could be flown if these three scenarios occur, or if one of these scenarios occur. So 408,240. So therefore there are 408,240 ways to arrange the flags. For B, we're going to change it up a bit by adding in a certain restriction. In this case, the restriction is if the host country is always on the far left. And we're still talking about 7, 8, or 9 countries attending. So again, we still see this or, so we should still think, okay, I need to be adding something here. But our cases are now changing. We still are going to have our 3 cases, right? So case 1, if we look at our 7 countries, our first spot is going to be taken because the far left has to be the host. And there's only one host, so there's only going to be one flag in that position. I'm going to multiply it because in this case, all these flags need to occur at the same time. So the first position and the second and the third and so on. So that's why I'm multiplying. And there are 6 flags remaining in 6 spots, so it's going to be 6 factorial. This works out to 720 ways. Case 2, or 8 countries. Again, same idea. The host is always on the far left. So the host is on the far left. One country is then removed, so that means there are 7 remaining for 7 other positions, or 7 factorial, which is 5,040. Case 3, you can kind of see the pattern happening here. We're dealing with 9 countries in this case. One of them is the host, so they're always going to be on the far left. Multiply by, I would have 8 positions for other flags, 8 countries to fill those positions, so 8 factorial, which we've already learned from the last part is 40,320. So these are the number of ways that I can have each case, or the flags arranged in each case. Because I'm looking at or, so it's case 1 or case 2 or case 3, in this case now I'm going to add up my 3 different scenarios. 46,080 ways to arrange the flags if the host country is always on the far left and still dealing with the 7, 8, or 9 countries attending. B, 3 players each cut 1 card from a standard deck, or basically they take 1 card or deal 1 card. If order is important, in how many ways could they be all hearts? And in B, how many ways could they be all aces? So you could do this in a couple of different ways. All hearts is what I'm going to start with first, but because 3 players are picking a card, that means I have 3 different positions. Player 1, player 2, player 3. If I'm looking at how many ways I could draw all hearts, that means I have to think about, well, how many hearts could the first player draw? Well, there are 13 cards, or 13 cards for each suit, so that means there would be 13 cards available, or 13 hearts that this player could pick. 1 would be picked, so then the second player would have 12, and the third player would have 11. I could also rewrite this as I have 13 objects, and I'm picking 3 of them. Right? Because again, this would be a permutation, order matters, and 13 objects picking 3. Either way we decide to do this, 1,716 ways. For B, all aces, same idea. we're going to have 3 slots or 3 positions. Player 1, player 2, player 3. Player 1 would have 4 aces, or could possibly pick 4 aces, multiplied by player 2, which would then have 3, and player 3, which would then have 2. Another way I could write this, I have 4 aces or 4 options, and I'm picking 3 of them. So again, 2 different ways we could represent it. If we wanted to, we could also use the permutation formula. Either way we decide to do this, we should find that there are 24 ways. C is asking, how many ways could we have all aces or hearts? Again, recognizing this or, we should think, okay, I need to add my 2 scenarios together. So we could think about, if we want to break it down, we could do it again into 2 steps. Let's say we didn't do the first one. If I look at aces first, well, 4, 3, and then 2 is the one scenario, plus how many ways could the 3 players draw hearts? 13 times 12 times 11. Additionally, you could think of the permutation. So 4p3 plus 13p3. And either way you decide to do this, you would get 1740. Is there anything we are not considering? And there is something that we're not considering, but we would have recognized this again when we've looked at other types of events. Right? In this case, there is an overlap. There is an overlap between aces and hearts, and in that case, there is 1 ace of hearts. So because there is that 1 overlap, I still need to subtract that. Because if one of those ace of hearts is already drawn, then I've kind of doubled up. Right? So I can't have all aces and all hearts together. Right? It wouldn't work. I wouldn't be able to draw 3 cards because one of those cards would already be picked. Right? So I have to remove that overlap, similar to how I've done it in the past. So ace of hearts is that 1 that I'm removing. So again, we still need to watch for overlap. So in this case, the actual answer is 1,739. So that's how many ways I can draw, or 3 players could cut all aces or hearts, or all hearts. One last example before we start, or before we finish. But before we get into this last example, today's code word is headphones. Again, today's code word is headphones. So with our last example, in how many ways could 11 players of a team be arranged so that the captain and assistant captain are not together? So a couple key things here. We have 11 members of the team, and we're looking for how many ways the captain and assistant captain are not together. So this would be a scenario of when are they kind of 1 spot apart, 2 spots apart, 3 spots apart, 4 spots apart, and so on. Right, so if I draw all my spots out, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So in this case, if we had, say, the captain and the assistant, captain is in the first spot, assistant would have to be in the second, but they could also be, in the third, they could also be in the fourth, or in the fifth, or in the sixth, and so on all the way down to 11, and the captain could then also move to the second, and so on. So there's many different scenarios here where they could not be together. And because we're in that case, it's or, so are they 1 apart, 2 apart? Does the captain start in 1, or does the captain start in 2, or does the captain start in 3, and so on? That gives us many, 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 many different scenarios that we would have to add up. So in some ways, we could use the indirect method. So again, still dealing with the idea of the rule of sum, where we would add them up, but then using that to help us understand that we could also use the indirect method, which we've used in the past as well when we've looked at simple probabilities. So the way we would use that is, one, we would need to figure out the total number of ways to order 11 people minus the complement to what we're looking for. So if we're looking for when they cannot be together, then the complement is when they can be beside each other, or when they can be together. And when we subtract that from the total, we would get the ways that they are not together. So again, just using that indirect method. So if we kind of work our way through this, or reason through this, let me just move this down. How many ways can we order 11 people in 11 spots? Well, that would be 11p11 or 11 factorial. How many ways can they be together, or can they be beside each other? If I look at my 11 spots, again, the captain and the assistant captain have to be beside each other. And we've talked about when they're beside each other, what happens is that they become kind of paired or glued together. So if they get glued together, they now count as one group, or one person, you could argue. So if I go back and count, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I now have 10 groups, or 10 objects that I'm trying to arrange, because the captain and the assistant captain count as one group when they have to be beside each other. So how many ways can I arrange 10 groups into 10 spots, you could argue? Well, 10 factorial. But we also have to consider that for the captain and the assistant, it doesn't say how they have to be arranged. It doesn't say that the assistant has to be first or second, and the captain can be first or second. It doesn't say. So if I look at these two individuals on their own, how many ways can I order 2 people in 2 spots? Well, it's 2 factorial, or basically 2 ways. So it's either captain and assistant, or assistant and captain. So I would multiply that by my 10 factorial. So they could be arranged throughout these 10 spots, and then within themselves, they could be arranged 2 ways. So this would then equal 11 factorial minus 10 factorial times 2 factorial. I get 32,659,200. So you could see there are many ways that they could not be together. And you can hopefully see that it would be very inconvenient to try to go through and add up each scenario where they're not together. And chances are we would probably get lost and confused before we even got close to figuring out that final answer, if we did it the direct way. So still taking into the idea of the rule of sum, but understanding that in some cases it may be easier just to use the indirect method. So again, still using the idea of the organized counting, the fundamental counting principle, factorials, permutations, but just adding in the idea, if we have multiple cases that cannot happen at the same time, we would add them together. Again, we've talked about this before in simple probabilities, so now we're just extending off of that and adding this concept into or onto what we've just been learning. If you have to go back and look at some of those simple probability notes, or if you have to go back to the organized counting or permutations and factorials, please make sure you do that so that you're comfortable with this material.